All right, AP Chemistry. This is your lecture lesson for Thursday, October the 3rd. It's going to take about 10 minutes or so, 10 to 15 minutes. I will quiz you on this tomorrow. There will be a quiz on this exact problem with the exact number. So I want to be sure you watch this and understand how to do this. So earlier this week, we had assignments where we calculated the empirical formula of a compound. That's the lowest ratio of atoms in that compound. So what we're going to do now is we're going to figure out how to use that to figure out the actual molecular formula. In other words, what's the actual formula of that molecule, not just the empirical formula. In order to do that, we need one additional piece of information, and I'm going to show you what that is. Okay, so the molecular formula of a substance can be found if we know the empirical formula and the molar mass of the substance before the combustion. Okay, so a molecular formula is the actual formula of the chemical compound. So we've learned earlier last week that if we have 1 mole of any gas, that 1 mole of any gas occupies 22.4 liters of volume at standard temperature pressure. Don't worry about really what standard temperature pressure is at this time. We'll get into that in the next couple of weeks. But we're just going to assume that we're at standard temperature and pressure. So that means 1 mole of any gas takes up 22.4 liters of volume. Because of this relationship, if we know that if we take the mass of 22.4 liters of our gas at STP, we will know that we have the mass of 1 mole, which is the molar mass. So again, we have a volume of 22.4 liters of the gas. We put it on a scale and we weigh it. And whatever that mass is of that gas that occupies 22.4 liters is the mass of 1 mole of the gas. So that's our molar mass. So let's say that 78.11 grams of an unknown hydrocarbon, that's a CH compound, occupies 22.4 liters. Since 1 mole of any gas equals 22.4 liters, the molar mass of that gas would be 1 mole of our gas, whatever that unknown gas is, equals 78.11 grams of that gas. With this additional piece of information, we can calculate the actual molecular formula of the molecule and not just the empirical formula. Okay, so here's an example. This is an example that you did on the day 25 homework assignment. So we're going to rework this. So you've already done this, and hopefully you still remember how to do it. So the combustion of an unknown hydrocarbon produces 5.72 grams of carbon dioxide and 1.17 grams of water. Determine the empirical and molecular formulas of the compound. So last time we did this on day 25, we only computed the empirical formula of the compound. So a hydrocarbon is a compound made of carbon and hydrogen. A combustion reaction burns a hydrocarbon and has the general formula, some CH, some sort of hydrocarbon, plus oxygen. You light a match to that, and it produces carbon dioxide and water. Okay, so let's go ahead and do this. We did this earlier. So we start off with 5.72 grams of carbon dioxide. So we have basically our boxes there. And we start off our equation with 5.72 grams of carbon dioxide. Now we have to convert that into moles of carbon dioxide. Anytime we're going to work inside of a chemical equation, we have to convert to moles. So the molar mass of carbon dioxide is 44.01 grams per mole. So that means that we multiply those two factors together, and that will give us the moles of carbon dioxide, which is 0.75 moles of CO2. What we want to know is not the moles of CO2, but the moles of carbon. We're interested in how much carbon is in the CO2 because all of that carbon had to come from our hydrocarbon compound, the CH, over on the left-hand side. So if we know how many moles of carbon we have in the carbon dioxide, we'll know how many moles of carbon we have in our hydrocarbon, CH. So there's 1 mole of carbon. If you look at the formula for carbon dioxide, there's 1 mole of carbon for every 1 mole of carbon dioxide. It's a 1-to-1. So we put that in our equation. And now we can go ahead and compute that there's 0.13 moles of carbon in the carbon dioxide, which means there's 0.13 moles of carbon over in our original hydrocarbon that we burned. Now we're going to do the same thing for hydrogen. We want to figure out how much hydrogen was in that hydrocarbon. And as you can see from the equation, all of the hydrogen went into water. It all went from the hydrocarbon all into the water molecule, or the moles of water. So we started off with 1.17 grams of water. We put that into our equation. We begin our equation with that. And then we have to convert that to moles of water, and there's our molar mass conversion for water that we've used many times before. So that tells us how many moles of water. And we see that for every 1 mole of water we want to make, we need 2 moles of hydrogen. In other words, for every 1 water molecule we want to make, we need 2 atoms of hydrogen. So we need twice as many atoms of hydrogen as we have water molecules, or same applies to moles. So that means we have 2 moles of hydrogen for every 1 mole of water. And if we do that calculation, we also end up with 0.13 moles of hydrogen. So the same number of moles of carbon as hydrogen. So we simply make a ratio out of that. It doesn't really matter which one you put on the top and the bottom, or the bottom, because they're both the same size. So you can see it's a 1-to-1 relationship. We could write C 0.13, H 0.13, but we have to convert that into whole number ratios. And you can see just by looking at it that it's going to be a 1-to-1 relationship. So that means our empirical formula is CH. Same number of moles of C as there is of H, and it's a 1-to-1, so it's CH. So this is where we left off with empirical formulas last time. Now we're going to go a step further. So this is where we left off on the day 25 assignment. Now we can use the following relationship to determine the actual molecular formula of this molecule. So multiply the subscripts of the empirical formula, it's 1 for C and 1 for H, CH, by this factor N. And the way we get this factor N is with this formula. We take the molar mass, and we figured that out earlier, it's 78.11. And we divide that by the empirical formula molar mass. Now what does that mean? Well, let's look at this. Earlier we determined that the molar mass is 78.11 grams. So the empirical formula molar mass is, the empirical formula is CH. So it's C1, and carbon has a molar mass of 12.01, and H1, and hydrogen has a molar mass of 1.01. So the molar mass for the empirical formula CH is 12.01 plus 1.01 is 13.02 grams. So now we can take those two numbers and put them into this formula, and we end up with the molar mass of 78.11 grams that we determined back at the beginning of this problem, and the empirical formula molar mass of 13.02, and that equals approximately 6. So what we end up with is the empirical formula was CH, and the actual formula of this molecule is C6H6, and that means the molecule is a molecule called benzene. So that's how you figure out the actual molecular formula. You get the empirical formula, and you use the molar mass of the compound, which you can determine experimentally, even if you don't know what the compound is. And then you apply those two to come up with the actual molecular formula. And once you have that, you can figure out what the compound is. And that's the end of this lesson. So I'm actually going to give you a quick quiz on this. Write this out a couple times, exact same numbers. I'm not going to change anything on this. And we'll do that at the beginning of class on Friday. All right, have a good evening.